Connecting sources in Y or delta. In this presentation, we're going to look at what the implications are when we take individual single-phase sources and we connect them in either a Y configuration or a delta configuration. So before we get going too far, we need to have a general understanding of what sort of three-phase sources, what sort of forms they come in. Three-phase sources are built or assembled really from individual single-phase sources. And the ones that we have most readily is alternators, transformers, and then finally inverters. Now let's take a look briefly at some of the connections that we may expect to see for transformers in either a Y or a delta formation. So let's look at Y first. This is an example of three individual single-phase transformers, and they're being supplied their rated voltage on the primary, and their secondaries are all interconnected together. The interconnection of those is in a star manner, where each of them is connected together with a common tie, and then we have individual line conductors coming off. So this would be a transformer bank that's assembled with three individual transformers with the secondaries connected in Y. The other way we could do the exact same transformers would be to connect them instead in delta. Now in delta, we're sort of connecting them all in series, and then we have an individual conductor coming off, again giving us A, B, and C. Now depending on which of these two orientations we choose, we're going to get a different output voltage from the transformers. The same thing will happen when we're talking about inverters. Now, this isn't done nearly as much as it was in the past, and that's because now we have solar PV inverters that can give us a nominal three-phase system voltage rather than trying to assemble our own three-phase connection by using single-phase inverters. Depending on the brand, we were able to assign each of the single-phase inverters to a particular line or phase, and then you had the choice. You could connect them in either Y formation or delta, depending on the voltage requirements and the application. Now, for this presentation, we're going to focus our efforts more on the more common application, which is the alternator. An alternator is one that has the individual three windings inside it, and when it's spun, will develop voltage on each of those independent windings. Now, often these windings are brought out to the junction box on the side of the alternator so that we have access to both ends of the winding. And that then allows us to connect them in either Y or delta. Now, it's important to realize that when the alternator shaft is spun, rated voltage will be induced into the winding, and the current rating that's given on the machine is the absolute maximum it can possibly supply. You cannot get more in this particular situation. You cannot get more than 5 amps out of each one of those individual windings. And so that's an important aspect to keep in mind. So let's take a look at this alternator and see what happens if we were to connect these windings in Y. When we connect them in Y, it would look somewhat like this. I've chosen not to place a neutral onto that star point as it doesn't aid in this example. But as you can see, there is a common point connection here and three individual line conductors. A Y-connected alternator, 120 volt 5 amps is the individual winding rating. If we were to break it down further, we would see that in fact, the line voltage between those individual line conductors coming out of the alternator, we have a voltage of 208 volts. The line current would be equivalent to the phase current. And as we can see here, the phase is 120 volt 5 amps because that's the rating of one of the individual windings. And so to back up everything that we've listed there, we could say E phase times root 3 gives us 208. The line current that we could possibly connect onto this particular alternator would be 5 amps. That's absolute max. And the S total is 1800 VA. E line times I line times root 3. All right, so that all makes sense. Let's then contrast that against the same alternator, but this time we're going to connect the windings in delta. When we connect them in delta, it can sometimes be a bit of a confusing wire. And because of that, you need to be very specific about how you connect these together. So I'm really connecting them all together in series to create one gigantic loop. And then I'm taking line conductors off each one of the individual terminals. Now remember, the alternator is connected in delta, but the individual winding rating is still only 120 volt, 5 amps. Now, due to this, let's see what we get for different values in our diagram. So here's our alternator connected up for delta. The phase continues to be 120 volt and 5 amps, and that's because it's the rating given by the manufacturer. The line conductors come off the junctions where we have connected the windings together. And what this then means is that we get a somewhat arbitrary or odd 120 volt line voltage, not really a common one that we would utilize very often. The line current, however, is a little bit more. It's 8.66 amps, and the reason for that is that each one of the individual windings is capable of 5 amps, and when they join at the junction, that increased value of current is then seen. We have a √3 increase. Notice that it didn't really matter if we connected the alternator in Y or delta, the S total still ends up at 1800 VA, and that's with the new line voltage and line current value multiplied by √3. So in closing, important to understand, when single phase sources are changed from Y to delta or delta to Y, the phase ratings remain unchanged. And if you can keep that in mind, it will be helpful as you answer different questions relating to this topic.